So double replacement is the fourth type of reaction. These are going to be where you have two compounds. So the way you'll recognize those is you're going to start out with two compounds. And just like in single replacement, not all of the reactions will take place. So sometimes you'll write no reaction depending on if a new substance is formed. Okay. So I have these rules listed here for you when to know if a double replacement reaction happens. First of all, if a new substance is created, it's going to happen. But if it's something that stays aqueous in solution the whole time, it's not going to happen. So if it makes a solid or a liquid or gas, it's going to take place. Generally, when we're mixing two compounds together, they're going to be aqueous. And do you remember from the beginning of this unit that we did before the break, when we listed all those symbols, what did aqueous mean? No, it didn't mean acid. It meant it was dissolved in water. Okay? It means it's a water type solution. So if I take sodium chloride and I dissolve it in water, that is now an aqueous solution of sodium chloride. Okay? And what happens when you dissolve sodium chloride or any of these ionic compounds that are soluble is they break apart. So now it's no longer a sodium and a chlorine stuck together. It is now in solution floating around, sodium ions floating around separately from chlorine ions. They are no longer bonded together in an ionic bond. They're now separate, which is why salt water conducts electric current, because you have those ions present. Okay? So if I dissolve two things and they both stay aqueous, and the interaction of them all stays aqueous, you actually get no reaction. You just have four different ions swimming around in solution. Okay? But if something is insoluble, then they react and they form a precipitate. And that's where I mix two liquids together, mix them together, and I get a solid. So that reaction would take place. So the way that we know which ones are aqueous, which ones are soluble, is we're going to look at these solubility rules at the bottom of the paper. Okay? So before we even start with the reactions, I want us to look at the solubility rules and see how they work. Okay? So, well, let me backtrack. Let me show you how you rearrange them first. Let me backtrack a little bit. So whenever I am rearranging these double replacements, when we were doing single replacement, I said refer to the activity series. A metal replaces a metal, a non-metal replaces a non-metal. In the case of a double replacement, they basically switch partners. And the best way to remember it is outside, inside go together in the product. So in this case, I'll take my outside and join them, and then I take my inside and join them. Okay? So it doesn't matter which one I write first. I can do the insides or the outsides. It doesn't matter. My habit is just to always do the outsides first. It's just what I do. Okay? So now I would make the two outside things that go together are going to be the sodium and the oxide. How would I write that formula? Na2O, okay? And how would I write the magnesium and the chloride together? MgCl2, okay? And then, of course, I would need to balance that by putting a 2 there, and then I'm done, right? Okay? So, same thing on the next one. Outside, inside go together. So I'm going to put together potassium and oxalate. So how would I put those two together? Okay, and then I would put together permanganate and sodium. So Na4. So I need to balance. So I put a 2 here and a 2 here, and it's balanced. Okay. So that's. I'm not saying if this reaction happens or not happens at this point. I just want you to see how we put them together. We put the outside things together. We put the inside things together. Okay. And then always double check that you put a positive and a negative together. Don't put two negative things together. Don't put two positive things together. Okay? Still always list the cation first and the anion second. Okay? So that brings us to how something happens. We already talked about those. If it makes a solid, a liquid, or a gas, then it's going to be a reaction that's going to occur. Okay? So what you're going to do with these is you're going to, just like we just did, we're going to predict what it makes. Okay, we're gonna, if we know it's a gas, we're gonna write a G behind it. If we know it makes a liquid, we're gonna write an L behind it. If it's something else, we're gonna go check the solubility rules, and we're gonna see whether it's aqueous, meaning it's soluble, it stays dissolved, or if it's a solid, which means it's insoluble because it forms a precipitate. And then we're gonna decide if they happen or not. Okay. Oh, that's the other thing. Also, whenever we do this, wait to balance it until you've checked your solubility rules. Because if everything's soluble and a reaction doesn't happen, you don't need to waste your time balancing it because it's a no reaction. So save yourself a little bit of time by go check your solubility rules first. If it's a no reaction, then move on to the next one. Okay? So let's look at our solubility rules. Okay? Let's talk about this real quick. Number 4, it says if water is produced. When water is produced, what kind of substance is that usually going to be? Solid, liquid, gas, or aqueous? Water is dissolved in water?
Is water wet?
It's going to be a liquid. So anytime water is formed, it's going to be forming as a liquid. Occasionally, if it's like a combustion, it might be a gas that it's going to be formed, but usually we say it's a liquid. We don't usually form solid water. We have to freeze it to get that to happen. Okay? So water being formed is always going to be a liquid. So that means that reaction will occur. And we'll talk about acid-base in a minute because they always form water. Okay? So these are your solubility rules. Okay? There's no way around it. You need to memorize them. Okay? And honestly, it's easiest to remember and memorize what's always soluble. Okay? Because no matter what it's with, it's always going to be soluble. Okay? So then you can worry about the other things. So group 1 metals, which is lithium, sodium, etc., and ammonium, which is the NH4+, are always soluble. No known exceptions. They're always soluble. Same thing with nitrates and acetates. Always soluble, no matter what they're bonded with. Okay? So if you see something that's got a group 1 metal, you don't even have to question what it's with. It's going to be soluble. So if it's soluble, we write behind it AQ because it stays dissolved in the water. So aqueous. Okay? If it is something that's insoluble, means it's going to make a solid. It's going to precipitate. And that probably is the hardest thing because we write down S, and what do you automatically think when you write an S behind it? Soluble. I know. They should have come up with some other things to name this because it gets confusing. But S does not mean soluble. It means solid because you're stating the state of matter that it's in, and it's a solid. Okay? So if you look at the chlorides, they are always soluble unless they are with silver, mercury, or lead. Okay? That's another one to make sure you know because that shows up a lot. Okay? So then if I was to put that down on paper, let's say I was going to write silver chloride, I would write AgCl, and then behind it I would write a little S for it makes a solid. Okay? Sulfates, always soluble unless it's with one of those things. Okay? Whereas the bottom of the chart, those things, carbonates, hydroxides, sulfides, they are always insoluble, meaning they make a solid, unless they're with one of those other things. Look at what one of those other things mostly are. The ones that are always soluble, like the group 1s, the ammonias, that sort of thing. Okay? So before we start trying to balance some equations, I'm just going to get you used to using the solubility rules. So let's just throw some of these out together and see what they are, soluble or insoluble. Okay? So let's start with, what if I have Pb2 plus and I have S2 minus? Okay? Would that compound be soluble, which means it's aqueous, or would it be insoluble, which means it would make a solid? So look at your solubility rules. It would be insoluble. So the way that I would write that is I would say PbS with a little S behind it for saying it's a solid. It forms a precipitate. Okay? What if I have sodium and sulfide? It's a group 1 metal. Group 1 metals are what? Always soluble. So we would write Na2SAQ behind it for aqueous, meaning it stays dissolved in the water. Okay? Ag and chloride, silver and chloride, what would it be? Insoluble. It's one of the exceptions. So we would write AgCl with a little S behind it. How about calcium and carbonate?
Insoluble.
It'd be insoluble. Look at carbonates are always insoluble unless it's with a group 1 metal or ammonium. Calcium is a group 2 metal, so we would say CaCO3 and then an S. Calcium carbonate is limestone marble. That's like what that is. Statues are made out of calcium carbonate. That's why acid rain dissolves them, because it reacts with it. Because it's actually fairly... Okay? So do you see how to use the chart at least? Okay? So now, go back up there and look at what we wrote for those examples and tell me what they would be. You should notice it really quick because they all have what in them? Yeah, well, the second one doesn't. I mean, the first one doesn't. But they have, the second example that we did had group 1 metals in it, right?
Yeah.
So those are going to all be soluble. So they're going to stay aqueous. I'm going to go back to it so y'all can look at it. So this one would for sure be no reaction, right? So write that next to it. Because group 1 metals right there. And if you're looking at a problem and you see that right off the bat, you don't even have to go through the trouble of writing the products if you don't want to. If you say, oh, group 1, doesn't matter, it's going to be no reaction. So I would just literally have a beaker full of all these little ions swimming around in there. Okay. What about the first one? Remember we said it made sodium oxide and magnesium chloride. They're all soluble, so this would also be a no reaction. Okay? Because everything stays soluble. Okay? We're fixing to do some of those. Yeah. So go to the next page where you have your examples and we'll do some of those. Okay?
Wait, so do we have to balance it?
Don't balance it until you know it makes a reaction.
So if it doesn't?
If it's a no reaction, move on because nothing's happening. So there's no reason to waste our time with balancing it because it's a no reaction. I mean, if it makes you feel better and you want to balance it, you are welcome to. I'm not gonna say you don't.
Wait,
No.
we have to memorize?
You have to memorize the solubility rules. I give you the activity series, but you do have to memorize the solubility rules. Okay, so on your examples, will you please just mark out number 1 because it wouldn't. I mean, mercury 2 chloride itself is just mark that out. Okay, so we're going to do number 2, which we have silver nitrate, which is AgNO3, plus we have potassium phosphate, which would be K3PO4. Okay, so we're going to put our outside and insides together. So we're going to get silver phosphate, which is Ag3PO4, and potassium nitrate. And we should be writing aqueous on these so that we recognize that these are aqueous. So now we need to look at our solubility rules to see what's aqueous, what's solid, if any. Okay? Doesn't matter which one you check first. I always go to my group 1s first because I know group 1s are always soluble, so I know that this one's going to be aqueous. Okay? How about the silver phosphate? Find phosphates on your list. What does it say about phosphates?
How do you know they're all aqueous?
Assume the first ones are aqueous.
Oh.
Yeah. For these, you can assume, for these purposes, you can assume your reactants are aqueous. It's your products we care about. Okay? So these are, I had a beaker of silver nitrate, I had a beaker of potassium phosphate, and I said, what happens if I dump them together? Psht. Is it going to stay aqueous, or am I going to get a solid out of there? Okay? If it stays aqueous, psst, nothing happens. Yes, I just get...
Your reactions, like, it doesn't really, like, you don't have to look at that part.
No, you're looking at the products. That's all we care about. Okay? So silver phosphate, is it aqueous? No, so it makes a solid, so we put an S. So this reaction will occur. Okay? So now, since we know it's going to occur, we're going to go ahead and balance it because we have to have a balanced equation. Okay? So how would I do that? 3 here and a 3 here. And now we're good to go. Yes.
So it's only aqueous if both of the products are, like,
Wait.
I got it.
Oh, okay. All right. So So
Assume the reactants are aqueous.
you assume the reactants are aqueous. Yeah, you don't have to question that. Only thing I'm wanting you to check are your products. Okay? All right, so let's do, let's do number 4. Calcium acetate, so Ca. Acetate is C2H3O2. We need 2 of them. Plus sodium carbonate, Na2CO3. So we're going to do our outside and insides together. So that means I'm going to make calcium carbonate. Go back and put your aqueous. Plus sodium acetate. Well, there I have sodium, which is always soluble, and I have acetates, which are always soluble. So I'm going to write my AQ. What about calcium carbonate? Soluble or insoluble? Insoluble. So I'm going to put that little S behind it. So now I know this reaction will occur, and so I need to balance it. So I need to put a 2 here, right? And I think that's all I need to do. Yes? You don't automatically know. And you have to show, so you have to label it because I need you to show me that you understand that that made a solid. And you need to label it because later on we're going to do net ionic equations and you have to recognize what's actually forming. Because you should label them all. Because later on when you get further into chemistry, they're not always aqueous. Sometimes there are other, and you have to be able to recognize that. So you need to label it.
So we just like assume making a worksheet, all the problems that we just assume, right?
The reactants,
Yeah.
you may assume the reactants are aqueous. Unless you're told otherwise. Like whenever I said, in some of those reactions we said iron metal. Is iron metal going to be aqueous? Common sense, what you're going to put behind iron metal? Fe is going to be a solid, yeah. Yeah. But for double replacement, these are a type of these are going to all be aqueous because that's what's going to mix. Double replacement doesn't really happen. There are very few double replacements that happen with the solids. We saw a really cool one at a demo at my conference that I'm going to try to see if we have the stuff to do because it was really cool. It was really, really cool. And that emphasis on the cool. Okay, so let's do another one. Let's do, we're going to do number 9. 9. So we have calcium hydroxide, so CaOH2, which is aqueous, plus phosphoric acid. How do I write phosphoric acid? Look at y'all go knowing your acids.
Yeah, that's me.
I'm impressed. Okay, outside, inside. So I'm going to make calcium phosphate. How do I write calcium phosphate? Oh no, Ca3PO4. 2. Plus, what's left? I got a hydrogen and I have a hydroxide. What do I make? I make water. And water is a liquid. Okay. So right away I know this reaction's happening because I made a liquid. Okay? But I still need to check my other compound. So calcium phosphate. Should I write an AQ behind it or an S? I'm going to write an S for solid. So now I need to balance this. I always balance the first thing I notice. So I notice, first of all, that I got 3 calciums and I only have 1 over here. So I'm going to put 3. Okay? Then I notice that I have 2 phosphates, right? I only have 1. So I'm going to put 2. So what should I put in front of water? Are you sure about that? 6. Give yourself a pat on the back if you said 6. Okay. Now, this is a special type of double replacement reactions. This is an acid-base reaction. Okay. Acid-base reaction. An acid, you should write this down at the bottom. An acid plus a base will give you an ionic salt plus water. Liquid water, to be specific. So if it's an acid base, you are going to have a reaction happen. Okay? You know how to recognize acids, right? They start with H, other than water. The way that you're going to recognize bases are going to have a hydroxide in them. And little ONH3. There's other bases, but those are the ones we'll see. But if it has a hydroxide in it and an acid, it's an acid base. So you know it's going to make, because it's going to make liquid water. Sometimes this will be a solid, sometimes it will not. Yes?
Does the base have to have OH? Because if it has NH, it looks like the acid doesn't have that O, it's just a hydroxide.
What? A base is going to be a hydroxide. For our purposes. There are some pseudo bases, but hydroxide in it or ammonia. Okay? I'll show you one without oxygen in the acid, though. It's how it's actually this. If I have NaOH plus HCl, what would that make? Sodium chloride and H2O. H2O is the liquid. Obviously, that's aqueous because it's sodium chloride. This is aqueous. There's aqueous. Also would happen because we formed liquid water. Even though that time the salt stayed aqueous. The NaCl stayed aqueous. And it would be a neutral solution, by the way. Strong acids and strong bases give you a neutral solution. Okay? Yes?
Don't some of those reactions give off heat? Give off steam?
Sometimes, yes. All reactions are either exothermic or endothermic. Some are so slightly so that they don't seem any different, but they're all reactions. There's always some sort of energy change in a chemical reaction. Sometimes it's just very slight. The majority of them tend to be exothermic, which they give off heat, but there are some that are endothermic. And they're cooler. Any other questions before y'all get started on your practice? All right.